All right. Quick question. If a country has more doctors, how is it possible that it has more death? Wait, what? How is it possible that a country with more doctors has more deaths? Well, it could be exactly the purpose of saying that correlation doesn't mean causation. Uh, Countries that have more doctors might be sicker to begin with. So today we're delving into one of the coolest methods in social sciences, which is differences in differences. Grab a cup of coffee, open your R Studio, and we're going to learn the basic intuition behind differences in differences. We're going to look at examples from economics, but also social sciences. Why should you trust me? My name is Bogdan Popescu, and I'm an assistant professor at John Cabot University. I also used to teach at Oxford and at Princeton. Over the years, I trained generations of undergraduate and graduate students in statistics and causal inference. So let's dive right in. Okay, so today we're discussing differences in differences, how to measure a policy's impact with data. So let's imagine that we notice that countries that have more doctors have more deaths. Is it possible that in countries where you have more doctors, you in fact have more deaths? So to what extent can we reach the conclusion that having more doctors, in fact, causes more deaths? In principle, if we think about logic, that should not be the case. It could, in fact, be the case that countries that are more sick or where patients are more sick are likely to hire more doctors. So, what we want to know fundamentally is what would have happened to those countries if they didn't have doctors. We want to think of a counterfactual in which the same countries didn't have doctors. So that is how we can think about the causal effect. We can think of on the one hand, about countries that had doctors and then countries that didn't have doctors. And then we can, in fact, measure the impact of the presence of doctors on the likelihood of deaths. So, in science and obviously social sciences, the idea of an experiment is the golden rule. So, this is what allows us to investigate the impact of a policy, or this is what allows us to evaluate the impact of a medicine. So, one group gets the medicine and another group does not. So, then this allows us to compare the outcomes. The problem is that in social sciences, we cannot really measure social science problems using the same principles of treatment and control group. So we cannot really switch a button and say these countries get democracy, these countries do not get democracy. So we can evaluate the effect of democracy. So if we cannot do that, we have to rely on what is called observational data. So these are kinds of data, so things that happen naturally, and we have to look for smart ways in order to mimic experiments. So the typical methods for natural experiments are differences in differences and regression discontinuity design. So differences in differences is a methodology that compares how things changed over time in a treatment group and in a control group. Regression discontinuity design compares units just above and below a threshold in order to investigate the impact of a policy on an outcome. Today, however, we'll stick to differences in differences. So we're going to start off with a traditional example that exemplifies the idea of differences in differences. So Card and Krueger are two economists that in 1994 tried to investigate whether raising minimum wage increases the number of jobs. So what they did, they looked at a policy that was issued in 1992 in New Jersey, according to which minimum wage raised from $4.25 to $5 per hour. In nearby Pennsylvania, the wage structure stayed the same. So you have these two neighboring states, on the one hand, New Jersey, and on the other hand, Pennsylvania. In New Jersey, you have an increase in minimum wage. In neighboring Pennsylvania, you don't. So the researchers, Card and Krueger, they looked at fast food restaurant jobs before and after this policy. So what they noted is that before the change in New Jersey, there were 20.44 jobs per restaurant. After the change, this number of jobs increased to 21.03. So if we do the difference, we notice that this is an increase of 0.59 per jobs per restaurant. So the question here is, did raising minimum wage cause this positive 0.59 per capita per restaurant increase? So not necessarily is the answer, although you might be tempted to say yes. It's not necessarily the case. It could be the case that restaurants might have hired more people in that year for a variety of reasons. For example, maybe a new mall opened or the economy improved. So we cannot really say for sure that it's really this policy of raising minimum wage that caused the increase in the number of jobs. So to figure that out, or to answer the question of whether it's really this minimum wage policy that caused the increase in jobs, Card and Krueger look at the neighboring state of Pennsylvania. So in this state, the minimum wage, as we discussed, did not change. So in Pennsylvania, after this change that happened in New Jersey, was 21.17 jobs per restaurant, whereas in New Jersey after it was 21.03. So if we look at the difference between New Jersey and Pennsylvania in the period after the implementation of the minimum wage policy in New Jersey, we get a difference of negative 0.14. So here too, we might be asking the question whether this is causal. The fact that there is a difference between Pennsylvania and New Jersey in the aftermath of the implementation of the minimum wage policy, can we look at this as causal? And the answer is no, because we're only looking at the effect after the policy. So we're also comparing two units, so New Jersey and Pennsylvania, that despite their proximity could be very different from each other. So we do not know whether it is actually the policy that makes a change versus intrinsic differences between these two states. So what we need to do is to look at number of jobs per restaurant both before and after in order to see the real effect. So just to be more systematic here, we have two groups, a control group and a treatment group. So in our case, this would be the control group will be Pennsylvania, the treatment group would be New Jersey. We have the number of jobs before, so this would be the not treated group A, so this is Pennsylvania before, and we have the treated group B afterwards. We also have the treatment group, which is New Jersey before, so this is C, and New Jersey D in the aftermath of the implementation of the minimum wage policy. So what we're trying to estimate here is the average effect on the treated group. How much the treated group changed because of this policy, so because of the minimum wage law, beyond what could have happened without this policy. So notice the difference in this table here. So what we're trying to estimate is the difference between before and after. So notice I marked that column in red. So I did B minus A. Remember that B represents the control group in the aftermath of the implementation of the policy, whereas A is the control group before the implementation of this policy. D minus C represents the difference between the treatment group afterwards and the treatment group before the implementation of the policy. So this difference, after and before, B minus A and D minus C, is called within unit change. I hope that is straightforward why this is called within unit change. So we're looking at what the minimum wage is, what the number of jobs per restaurants were in Pennsylvania, both before and after, and the number of jobs per restaurant, both before and after within New Jersey. So that's why this is called within unit change. We also want to examine the difference between the treatment and the control group. So we want to do what is called a cross-group change. So we want to measure C minus A. Remember that C is the not treated group in the treatment group. So essentially, New Jersey prior to the minimum wage law, and D and A is really the control group also prior to the implementation of minimum wage law. And then D minus B is really D represents the treatment group after the policy gets implemented, whereas A represents the control group after the policy is implemented. So once again, the C minus A and D minus B represents the cross group change. So we can have D minus C minus B minus A, which represents the within units change, or we can also calculate D minus B minus C minus A, which is the cross group change. Notice here how we can use them interchangeably. So if we do the calculation, if we apply this to the Card Krueger example, so remember that in the control group, we have 23.33 jobs per restaurant before the implementation of the minimum wage law, and we have 21.17 jobs after the implementation of the minimum wage law. But remember that within the control group, within Pennsylvania, there is no change in the minimum wage law. In the treatment group, which is the New Jersey group, we have 20.44 jobs per restaurant before the minimum wage law, and then we have 21.03 jobs per restaurant after the implementation of this policy. So notice that we have a difference here of 0.59 and then a negative difference here of 2.16. So if we do both the within unit change and a cross group change, we end up with these differences, which result in 2.75. So once again, what we're trying to do here is to estimate the average effect on the treated group, essentially how much the treated group changed because of the policy beyond what would have happened without it. Okay, so why this is controversial and why this paper was controversial in 1993 and 1994 is because conventional wisdom at that time suggested that if you increase minimum wage, you should see a loss in jobs because it's much more expensive to hire workers. So many companies would have decided not to hire more. So what they found in the Card Krueger's case is that employment, in fact, increased slightly in New Jersey. So this was contrary to what conventional wisdom said before their finding. But the innovative part, and the reason why Card Krueger is so widely cited today, is because they are one of the first people to think about this notion of a natural experiment. So this is really the whole logic behind the differences approach. So using observational data in a way that mimics a real experiment. So just to visualize this even better, so imagine that you have AB. Remember that AB is the control group. So this is the state of Pennsylvania. You have this linearity over time. And what's interesting is that you also have CD, which represents, C represents New Jersey prior to the implementation of the minimum wage law, and then D represents New Jersey after the implementation of the minimum wage law. So what is an increase in the number of jobs. But to visualize the causal effect, you can think of a counterfactual. So what would have happened had it not been for this minimum wage law? This is what would have happened. So you have this continuous blue line in the aftermath so without the implementation of minimum wage law, you would have continued to see a stable, probably increase over time, but not as much as it was with the implementation of the minimum wage law. So that is why the difference between this parallel line is really the causal effect. So I hope this makes it very clear, at least visually, how differences in differences work. So this allows us to see what is the causal effect of this policy change. So we can estimate the causal effect by using the following model. So we can write this econometrically in this manner. So you have a dependent variable, yit. So the subscripts it represent the cross-section and the time unit. So in this case, we're dealing with panel data. So the I is the index that captures the unit of analysis. In our case, the Card Krueger example, that would be the state. And T represents the time unit, whether it's before the implementation of the program versus afterwards. And then we have a series of coefficients, beta 0, beta 1 multiplied by group, beta 2 multiplied by time, and then beta 3, where you have the interaction between group and time. So this is, for example, what this would look like in an R code. So you have the outcome of interest, the dependent variable. You have the group. So essentially, an identifier, whether it's in the Card Krueger example, whether it's New Jersey or Pennsylvania. We have a time period. So whether it's before or after. And then we have the interaction between the group and time. Okay, so just to be even clearer, so group equals 1 if this is the treatment group. So meaning if this is the group of observations that receives a treatment at some point in time. Time equals 1 if this is the period after the intervention. And then what we're looking at first is beta 0, which represents the mean of the control group in the pre-treatment period, right? So in our case, this would be Pennsylvania in the pre-treatment period. The beta 1 is the increase in outcome across groups. So what the difference is between Pennsylvania and New Jersey. Beta 2 is the increase in outcome within groups. So how much this is increasing within Pennsylvania and within New Jersey. And finally, the part that we're interested in is really this interaction, group and time. So this is the differences in differences effect. So let us look at this more carefully. So we have the control group and we have the treatment group. So we have what Pennsylvania looked like before the implementation of the program, what Pennsylvania looked like after the implementation of the program, and then we have the treatment group. So what did New Jersey look like before the implementation of the program, and what did New Jersey look like after the implementation of the program? So if we look at all these elements, so the difference between the treatment and the control group, we have beta 1 because beta 0 cancels out. And then if we look at the difference between these two, clearly this and this are the same. So that's where we're left with only these two values. Here they are, right? So we can also do, so then if we do the difference before and after, we're left with these coefficients. So once again, the difference within units minus the difference across group is really what we call the differences in differences, or the causal effect. Okay. So one of the most important assumptions behind differences in differences is what is called the parallel trends assumption. So the treatment and the control group have to have the same trends prior to the intervention itself. So we assume that if it hadn't been for the intervention, the treatment group would have followed a similar trajectory to the control group. So we assume that the treatment group would have changed like the control group in the absence of the treatment. We cannot really prove this per se, but we can make it more believable with pre-policy data and with some context. It's also important that sometimes units can receive treatment at different times, which would complicate the analysis further, but we're not going to discuss too much. We're not going to discuss this too much today, but let me just show you some example. This is an example where parallel trends holds. So this is, for example, you can see here that prior to the intervention, parallel lines. This is also an example where parallel trends holds. So you can see that you've got 4 time periods. You've got 1, 2, 3, 4, and you notice that the treatment and the control group look very similar in time 1 and in time 2 prior to the intervention. This is an example where the parallel trends assumption is violated. And it's violated because clearly these two lines are not parallel. This is also an example in which the parallel trends assumption is violated. This is an example of parallel trends assumption holding, but it's also an example of units receiving treatment at different times. So this is something that could distort our differences in differences analysis. Notice that we have an intervention here and we have an intervention here on the control group. There are specific things that we can do. So for example, once again, this is an intervention and this is another intervention. Excuse me. So to handle these kinds of situations, we can use cohort-wise comparisons, Sun and Abraham, or Callaway and Santana. This is something more advanced that I'm not covering in this lecture. I'm now going to move on to some real world scenario. It is based on made-up data. So let's imagine that the World Bank is trying to reduce the risk of malaria in Malawi by providing insecticide-treated bed mosquito nets. So let's imagine that they provided insecticide-treated bed nets only to City B from 2017 to 2020, and the World Bank selected 24 individuals over 3 years from City B, and they wanted to see if the people who get these mosquito nets, whether that reduces their risk of malaria. So you can download the insecticide malaria dataset by clicking on this link. That's going to take you to a Dropbox link. You can download the CSV file and then you can run it on your own machine. Once again, this is made up data. So that this data doesn't really reflect any reality on the ground. So we have 8,000 observations. So if you click on show code, I'm showing you here how to load the CSV file and how to observe the first 10 variables. So we're dealing with 8,000 observations. We have multiple years, 2013 all the way to 2020. We have a bunch of variables that reflect people's level of income. We have their age, we have their gender, we have a number that reflects risk of malaria. We have some IDs. Notice here that this represents an individual identification for every unit. We have then some coordinates, like where these people are located, and then we have an indicator for the treatment period, whether this is before or after. And then we have city A and city B, which is not visible here. But remember that the treatment group is really city B. Okay, you can also download the shapefiles here to produce a map that looks like this. So to produce a map of malaria or where the experiment is taking place. So I just mapped it so that you can visualize this notion of differences and differences more effectively. We have two cities, City A and City B. City B is the one that receives the treatment. And what this map also shows is the risk of malaria, right? So circles that are bigger in diameter have a higher risk of malaria. You can see exactly the code here, how I produced this map. So hopefully just by clicking on show the code and clicking on this icon, you should be able to fully replicate this map. Okay, before we conduct any sort of analysis, it is always important to run a summary statistics analysis. So to get a better sense of what types of variables we're dealing with, how many unique observations we have, if we have any missing observations, what is the mean and standard deviation, the min, max, the median, but also it could be important to see if the variables are normally distributed or not, right? So for example, we notice that income, it's pretty normally distributed, which is a bit unusual given that income usually is left skewed, meaning there's very few rich people and most people are very poor. And we can notice here that, for example, age is right skewed. So that means there's many more young people compared to older people. Okay, so we have all these variables. Moving on, this is what we're trying to estimate. Just as a reminder, we're trying to estimate beta 3, which is the interaction between the treatment group and the time. So in our case, this is what this looks like. We have malaria risk as an outcome. Notice as before, we have these subscripts, I, T. So I is really the index that captures the individual that we're dealing with. And T is the time period. Remember that we have data from 2013 until 2020. So we have beta 1, which is the coefficient for just the treatment group. We have beta 2, which is the coefficient for the time period. And we have the interaction between city B and time T. At the very end, we have the error term epsilon IT. This is how we can calculate this beta 3. We simply take a linear model. We have the outcome of interest, the dependent variable, which is malaria risk. And then we have city, after, and the interaction between city and after. All the other things are just simple options in order to make the table look more readable. So if we run this analysis, this is what we get. So once again, this code here will produce a table that looks like this. So here, these are the independent variables. These are the coefficients. What's in parentheses are the standard errors. We have the number of observations in the analysis, and then we have the R squared. So how do we interpret this? So let us look at city B. So the interpretation here is that before 2017, city B had about 3 points higher malaria risk than city A. After 2017, right? So remember, 2017 is the year when the program gets initiated. Malaria risk in city A fell by about 4.5 points, as indicated here. And after 2017, malaria risk in city B fell by an additional 7.6 points compared to city A. So this is really the causal effect of this mosquito net program initiated by the World Bank. So this is, for example, what this looks like if we were to draw an event study plot. So this is, for example, how to obtain this code. It's simply a calculation of the mean risk by year and by city. And right, so this, I guess this is unnecessary. So we only need to do this once, and this is going to get us this. So the red line represents the trend for city A. Remember, this is the city that doesn't receive the mosquito net treatment. The green trend is really the trend for city B. Remember, city B is the one that in 2017 receives the mosquito net intervention. So what is interesting and what's absolutely visible with the naked eye is that there is a substantial decrease in the risk of malaria in city B after receiving the treatment, after receiving the mosquito nets. Okay, so what do we take away from here? Fundamentally, differences and differences are really about estimating a causal effect when we cannot run an experiment. So what we want to do, we want to compare changes over time in a treated group to changes over time in a control group. So we're interested in the difference between D and C and B and A. So D and C is the changes over time in the treated group. B minus A is the changes over time within the control group. So the key assumption, however, within differences in differences is this parallel trends assumption. So without this assumption holding, treated and control group would have followed the same trend. So just a reminder that what we're interested in if we were to run the model is really this interaction between group and time, which is beta 3. So this is called the differences in differences effect. I hope you enjoyed this video. If you found it useful, please don't forget to subscribe, give this video a thumbs up, and please comment down below if there's something in particular in relation to R that you'd like me to make a video about. Thank you and see you soon.